So in this video, we're going to talk about VLANs, which are virtual local area networks. A VLAN is the primary tool that we will use to implement network segmentation without purchasing separate physical hardware for every zone. Understanding how VLANs work is essential because they're the foundation of every segmented OT network architecture. And they'll appear constantly in network diagrams, firewall configurations, and security discussions. In the past, separating networks meant separate cables and separate switches. If you wanted your PLC network to be isolated from your engineering workstation network, you ran different cables to different switches and never connected them. That physical separation provided real isolation, but it was very expensive and very inflexible and impractical to do at scale. A VLAN divides a single physical switch into multiple logical networks. You configure each port on the switch as a member of a VLAN number, say VLAN 10 or VLAN 20. Ports assigned to VLAN 10 form one logical network. Ports assigned to VLAN 20 form another. Even though all those devices are physically connected to the same switch, devices in VLAN 10 cannot communicate directly with devices in VLAN 20. The switch handles the isolation in software. This gives you network separation without separate infrastructure. One managed switch can host several isolated network zones, each with its own address space, its own traffic rules, and its own security characteristics. Incidentally, you would have a router that would have to control the traffic between those two VLANs, and you can even implement firewall rules between those VLANs. So each VLAN is a separate broadcast domain. In networking, a broadcast is a message sent to all devices on a segment. ARP requests, which we covered in an earlier module, which is the mechanism devices use to discover each other's MAC addresses, are broadcasts. On an unmanaged or flat network, every device sees every ARP broadcast from every other device. On a VLAN segmented network, broadcasts stay within the VLAN. A device in VLAN 10 sends an ARP broadcast, and only devices in VLAN 10 see it. Devices in VLAN 20 don't receive it at all. For traffic to cross from one VLAN to another, it must pass through a layer 3 device, which I mentioned a second ago is a router, or a managed switch with layer 3 routing capability. That routing point is exactly where you place a firewall or access control list to decide what is and isn't allowed to cross. The VLAN creates the zone boundary. The firewall controls what passes through it. This is the key relationship. VLANs and firewalls can work together. VLANs create the zones. Firewalls will enforce rules between the zones. Neither one alone is sufficient. We'll cover firewalls in more depth later. A typical OT segmentation scheme using VLANs might look like this. Again, we'll have VLAN 10, which holds our field control devices like our PLCs and RTUs. This VLAN will get the strictest access controls. Only the historian server and the SCADA server are permitted to initiate connections into this zone on specific ports from specific source IP addresses. Nothing else is allowed to reach these devices. VLAN 20 holds operations equipment, SCADA servers, and HMIs. These systems need to communicate with VLAN 10 devices they pull, but they don't need to communicate with corporate IT systems. Access to this zone is tightly scoped. We'll create another VLAN, VLAN 30, which holds engineering workstations. Engineers need maintenance access to PLCs on a scheduled basis, but that access should be controlled, logged, and probably not always on. VLAN 30 might be permitted to reach VLAN 10 during a specific maintenance window and blocked at all other times. Another VLAN, maybe 40, might hold vendor equipment brought on site temporarily. Complete isolation from everything except the specific device the vendor is servicing. Again, think of it as the same physical building, but now we have walls and locked doors between our departments. The physical infrastructure, the cables, the switch, the space is all shared. The logical boundaries are now real and they are enforced. One important clarification, VLANs require managed switches. An unmanaged switch, the kind you might buy for under $100 and just plug into the wall, probably doesn't have VLAN capability. It treats every connected device as part of the same network. A managed switch has a configuration interface where you can assign ports to specific VLANs, configure trunk lines between switches, which a trunk line carries multiple VLANs, and set up the inter-VLAN routing rules. Managed switches cost more and require configuration, but in any OT environment where security is a requirement, you should have them. If you're accessing an OT network and you find unmanaged switches on the plant floor, that's something you ought to make a note of. Devices connected through an unmanaged switch are all on the same network segment, regardless of what the rest of the network architecture looks like. Any VLAN boundary that exists upstream of that unmanaged switch doesn't apply to the devices behind it. In the next video, we'll talk about why segmentation matters from a security standpoint, and what it actually does to an attacker who has gained a foothold in your network, and how it changes the picture compared to a flat network.